So today we're going to summarize second order linear homogeneous differential equations with constant coefficients. So A, B, and C are numbers. And homogeneous or homogeneous just means the right-hand side is 0. And recall that we're looking for solutions in the form e to the r, some number, times x. I'm calling the independent variable x. Okay. And if you differentiate this a couple times, I won't go through the derivation again. You can solve for r, and you get what you call the characteristic polynomial here. So y double prime becomes like r squared, y prime corresponds to r, and then y just corresponds to r to the 0. Then we solve for r. Okay. And then, because it's a quadratic, there are 3 cases. Case number 1, we could have real distinct roots, in which case the fundamental solution set looks like e to the, so suppose r1 and r2 are not equal, and they are real numbers, so real roots distinct. And this is a good fundamental solution set in that case. Number 2, we have a real root, but that has multiplicity to it, so it's a repeated root. So r1 and r2 are just the same number r. That's a real number. So in this case, using reduction of order, we found that this is a fundamental solution set. So by multiplying e to the rx by x, we guarantee linear independence of the 2 functions, and we also saw that this satisfies the differential equation. And finally, the other possibility is that your roots or your quadratic are not real at all, but they're complex, right? And we know that complex roots always come in conjugate pairs. So you have complex conjugate. I mean, for a quadratic, they come in conjugate pairs. So R1 is, let's call this alpha plus I beta. Alpha is the real part, beta is the imaginary part of our complex root, and R2 would have to be the conjugate. And in this case, a fundamental solution set is e to the alpha x times cosine beta x, and e to the alpha x sine beta x. So those are the 3 cases for your second order linear homogeneous differential equation with constant coefficients. Okay. So let's go, well, let's look at examples of each case. So let's look at the case number 1. So it's real distinct roots. So we have a second order differential equation, homogeneous. Suppose we also have some initial conditions. So we write down the characteristic equation. Here we can indeed, I believe, factor. And then we see we have 2 real roots, and they're different, they're distinct. So a fundamental solution set here would be e to the root times x, and then e to the root 2, right? The second 0, I guess. Okay. Those are linearly independent. They're not like terms. Okay. And our general solution for y is some combination of the fundamental solution set. And if you want a particular solution to the initial value problem, we'll go ahead and use our initial values in here for a second order differential equation. We need, we're using an initial value for y and its derivative. So I'm just going to differentiate. Okay. And then we see that y of 0 is a -1. Okay, so when x is 0, y is -1. So we get that y plugging into equation A, I guess. -1 is A plus B, right? Because of course, when x is 0, our exponential e to the 0 is 1. And then B, we'll use the next condition. Okay, so when x is 0, y prime is 12. And then we solve the system for AB. Okay, I'll probably use matrices. So here's the, I'll write this as a matrix equation. And that should be equal to the column -1, 12. And then I'll just use maybe method of inverses. So AB is the inverse of this matrix. So 1 over the determinant. So 2 plus 5 is 7. Okay. So 1 over the determinant. We're going to exchange the diagonal entries and then change the sign on the off diagonal entries. So it multiplies column on the right hand side. So it looks like A is -2 and B is 1. So now our particular solution to the initial value problem is where A is -2 and B is 1. That's just so easy enough. Case 1, real distinct roots. So now we're going to go to the second case, real but repeated roots, with an example. Case number 2, real repeated root. So here's a differential equation, constant coefficients, homogeneous. And we have some initial conditions as well. So we write down the characteristic polynomial, and this is indeed a perfect square. If you'd like, the root is -4 with multiplicity 2. So we found that one solution is e to the r times x. The other one is x times e to the -4x. That's our fundamental solution set. Our general solution is some combination of these two independent functions. So this is our general solution. Now I'm going to use the initial conditions to solve for A and B, but I need to know the derivative of y first, using the fact that y at 0 is 3, but A must be 3, right? Because x is 0. And then we use the derivative. So y prime at 0 is -13, get -4a plus b. And because x is 0, that term just goes away. But we already know that a is 3, so b must be -1. Okay. So now our particular solution to the initial value problem is a times y1 plus b times y2. Okay, so finally we can go to the third case. We have complex roots. But before we go there, let's look at a simpler case where the roots are purely imaginary. So here's a differential equation. You love it, you know it. Second order linear constant coefficients, homogeneous. So the characteristic equation, be careful here. We could write this as y double prime plus 0 times y prime, just in case you missed that, right? So the characteristic equation would be r squared plus 9 is 0. So r squared is -9, so r is plus or minus the square root of -9. It's 3i. So those are complex roots, purely imaginary. The real part is 0. So one fundamental solution set would be e to the 3ix, and the other one is e to the -3ix. But it might be the case that this differential equation is modeling the real number kind of phenomena. So we probably maybe want to rewrite this in terms of just real values. So the idea is that if you choose a new solution to be e to the 3ix plus e to the negative 3ix divided by 2, and y2 is e to the 3ix minus e to the negative 3ix divided by 2 times I, you might recognize these as the exponential form of cosine and sine, respectively. So this would be cosine of 3x, and this is sine of 3x. Okay, so we have, and these are going to be independent on the number line. So so here's another fundamental solution set. Right? Notice that it's in terms of real numbers, right? There's no I in there. So this is probably the preferable one. So our general solution would be some combination of sine and cosine. Okay, and I believe I have initial conditions, so I forgot to write them down, but when x is 0, y is 3. And when x is 0, y prime is negative 3. So we're going to need to use the initial conditions. We need to know the derivative of our function. So using a, we get that y is 3 and x is 0. Conveniently, a sine of 0 is 0. So we get that cosine of 0 is 1. So we get that a equals 3. Using the second initial value, we get negative 3a sine of 0. So that's going to go away. Plus 3b sine of, wait a minute. Okay, derivative of sine is cosine, folks. Okay, so that's 1. So you get that b must be equal to negative 1. So now our solution to the initial value problem, a times the cosine plus b times the sine. I guess we could mention that this indeed does form our formula for the case where your characteristic equation has conjugate pairs for the roots, the complex conjugate pairs. So this would be, so alpha here, alpha is 0, beta is 3. So we get e to the alpha x times cosine beta x, and then e to the alpha x times sine beta x. So since alpha is 0, I get e to the 0, so that just goes away, and beta is 3, so where we have complex roots again. All right, so complex roots. So third case again, we have some initial conditions. So we have the characteristic polynomial, which we can't factor, so just go ahead and use a quadratic formula, minus b plus or minus the root of b squared minus 4 times a times c, all divided by 2a. So indeed, our roots here are complex conjugates. I guess this is called repetition, right, in pedagogy, but so we have that our solutions are, this is a fundamental solution set, e to the power, which is the root, times x, and e, and then to the conjugate root. So notice this can be using properties of exponentials, but we don't want to, we want our solution to be real, right? We don't want any complex numbers there. So we're going to call y1 of a new fundamental solution set, and y2 we're going to call this, it's going to be the sum of these two, and we're going to divide that by 2. And then for y2 we're going to subtract the two solutions and divide by 2i. We note that e to the 2x is a common factor, so we factor that out, and then we want to recognize this business as the as a way to express cosine of 3x using exponentials. So y2 similarly, factor out the e to the 2x, and the remaining part you'd want to recognize as the exponential way of expressing sine of 3x. So here's a different fundamental solution set, and that's the way we want to, that's the one we want to use. And this is a since our root is alpha plus or minus I beta, where alpha is 2, beta is 3. We can also see that this conforms with our formulas for the complex conjugate root case. E to the alpha x times cosine beta x. E to the alpha x, then times sine beta x. So, oh boy, do we really want to use initial values here? So here's the general solution, some combination of the fundamental solution segments. I don't know, I almost prefer leaving it in complex exponentials, but so using the initial condition that when x is 0, y equals 1, conveniently sine of 0 is 0, cosine and this stuff is 1. So you now know that a equals 1. And then we're going to use the second condition, but for that we need to know the derivative. So maybe towards that end, I'll just factor out the e to the 2x. Right? I mean, it doesn't make it that much easier, or even easier at all. But it's just that I kind of conceptualize this just using the product rule on once, if you will. So differentiate the exponential, leaving the business alone, and plus leave the exponential function alone and differentiate the trig stuff. And we know that y prime at 0 should be 2, according to the initial values that are given. So y prime is 2, x is 0, so you're left with 2a plus 3b. Oh, 2a plus 3b, sure. That works. So if a is 1, then b must be 0. So here's our solution to the initial value problem. A is equal to 1 times y1, and b is 0, so whatever, it's not there. All right. So to summarize, we just went through the 3 cases where you have your second order differential equation, constant coefficients, linear, homogeneous, distinct roots, real roots, and then we have repeated real root, and then the roots are complex conjugates. So next we want to talk, so the second part of the program here is to talk about second order linear but non-homogeneous, so the right hand side is not 0, differential equations, but with constant coefficients. And in particular, we're talking about the right-hand side not being 0 and of a particular form. Okay, so maybe I can start that. Okay, so now the right-hand side is not 0, it's some function of the independent variable, which I'm calling x. So remember that this is this is very analogous to how we solve matrix equations in linear algebra, ax equals b. We found that any solution can be written as a solution to the homogeneous version. So on the right-hand side, we get the 0 vector. And then we find a particular solution to the original non-homogeneous equation. And then we say that in the general, the solution is a combination of the homogeneous, or a sum of the homogeneous in particular. Because a times x here would be a times the homogeneous plus a times the particular. A times the homogeneous gives you 0, and a times the particular solution gives you b. So similarly here, we have a linear operator on y. It's a linear operator. It's just differentiation and multiplication, so by constants, and then it's equal to a right-hand side which is not 0. So we first find a solution to the homogeneous part, and then we find a particular solution to the non-homogeneous part. And then the general solution, y as a function of x, would be the homogeneous plus the particular. And so we're going to be focused on how to find, there's different methods that you're going to learn to find a particular solution to a non-homogeneous equation. And the first method is called the method of undetermined coefficients. And it's used to find a particular solution, okay, where the g of x here is of a particular form. It can't just be any function for this method. It's restricted to a simple class of functions, or a class of functions. So it's going to be some sort of polynomial, possibly, times some sort of exponentials of the simple type. So I mean, like e to the ax type, okay? Not e to the ax squared or something like that. It's very basic exponential. And then times either sine or cosine. So that's an important restriction, that we're only going to use this method if on the right-hand side we have polynomial, exponential, sine or cosine, or some product of those. All right. So suppose we have, let's do the polynomial first. So the right-hand side, we just have a polynomial. It's a polynomial of degree 2, or order 2, whatever. So what we're going to do is, first we're going to find the homogeneous part of the solution. So that's kind of the first step, find homogeneous solution, or the solution of the homogeneous part. So I'm going to write down the characteristic polynomial. Here we can factor. So r is either -3 or 2. So our homogeneous solution here is some combination of these exponentials using our roots. So now we're in the business of finding a particular solution to the original. So what you want to do is you want to look at the right-hand side and say, okay, it's a polynomial of degree 2. So we're going to assume that we can find a particular solution of the form, except this should be x, I guess, since I'm using x. It's my independent variable. So that would be a second-degree polynomial. So you assume that the particular solution is just some second-degree polynomial, and so you don't know what this polynomial is, so you have kind of general form or generic form of the second-degree polynomial. Now, let me write down the fundamental solution set. Now, notice that every term, and I mean every term, right, in the particular solution is linearly independent from anything in the fundamental solution set. That's key. So if that's the case, we're good to go. And I'll show you what to do when it's not the case in the next example. So these are, every term in the particular solution is independent from anything in the fundamental solution set. And a simple way to think of that is that they're unlike terms, right? You can't combine anything in the particular solution with something in the fundamental solution set. So now, how do we determine? So what are the undetermined coefficients? Well, these guys, obviously. Now, so how do we undetermine them, right? How do we determine the coefficients? Well, usually when we assume something might work, when we think something might work for a differential equation, we're going to differentiate it, the assumption, if you will, a couple times, and then plug this back into the non-homogeneous original differential equation. So we get y double prime plus y prime minus 6 times y, and that we want that equal to x squared plus 1. So now I'm going to simplify by gathering all the like terms here. So you have the x squared term, you have the x term, and then we have the constant term. And that has to equal to 1 times x squared and 0 times x, in case we miss it, plus 1. Right? So of course, for these two polynomials on the right and the left-hand side here to be equal, means that they have to be equal for all possible x's, right? So that requires us to say that the coefficients for the x squared terms on either side are equivalent, and then the coefficients for the x terms on either side are equivalent, and the constant term here, constants are equivalent as well. So you get a system of equations and unknowns. It's a linear system, so I'm not going to bother too much, right? I see that A, I'm not going to use something fancy like matrices, so A is -1/6. So from the second equation, we see that B would be negative 1/18th, and if B is negative 1/18th, then C will be let's see, 17 over 8. Sorry, 19 over 18 divided by negative 6. 60 and 48, 108. And these don't have to be pretty, but we've determined the coefficients, right? We know A, we know B, we know C. Then don't hold me to this being correct, unfortunately. So now we have a particular solution. So now the general solution is the homogeneous part plus the particular part. So the homogeneous part we see is that combination of the fundamental solution set. The particular part is just a polynomial degree 2. And so this is a general solution. Any solution can be expressed in this form. All right, let's keep going with let's look at an exponential. So so this time the right-hand side is going to be some sort of exponential, and we'll compare 3 cases. So here by exponential, I mean the right-hand side is just some simple exponential function. All right, so we know that the homogeneous part is going to be the same for all 3. And we already know the fundamental solution set because it's exactly the problem that we did previously. Homogeneous part at least. So now, if this is the homogeneous part, our next task is to find a particular solution. So let's start with the first one here. It's called number 1. So the right-hand side is just a simple exponential. So what we assume is that a particular solution here is going to be that simple, some multiple of that simple exponential. And now the thing to notice is that the e to the 4x is unlike or linearly independent with everything in the fundamental solution set. You cannot combine those. So we're good to go. We have assumed a good form for our particular solution. And to see what a has to be, of course, we're just going to differentiate a couple times and then plug that into our original non-homogeneous equation. So y double prime plus y prime minus 6 times y should be the right-hand side function. So notice that e to the 4x just cancels out everywhere. And so we're left with some number of a's on the left. We solve for a, so we have a good particular solution, a times e to the 4x. Okay. So now we combine to get a general solution to the original problem, we just combine the homogeneous part with a particular part. So let's look at the second case, right? So we already know the homogeneous solution, a general solution to the homogeneous part. So now we're going to find a particular solution, and we see the right-hand side is a simple exponential, so we assume that it's going to be, our particular solution is going to be some multiple of that exponential. But then notice that this is not unlike, right? This is like something in the fundamental solution set. This is just a multiple of that. So we must insist that the particular solution cannot be a multiple of something that's or some combination of the fundamental solution set, right? Because we know that if you plug that into the differential equation, you're going to get the right-hand side as 0. So to guarantee independence, we're just going to multiply by x to make sure that this is now independent from that. And you can use the Vronsky, just to quickly see that indeed these would be independent. Compute the determinant here, minus. So indeed that's always positive, so it's never 0. Okay, so we have independence. So that this multiplication by this single factor is just to make the particular solution linearly independent from everything in the the fundamental solution set. So now, once we have a form for our particular solution, right, you're gonna, the laborious part, differentiate and plug into the original. So So I'd like to go ahead and tidy this up, right, a bit. So we have a, say, think of that as a polynomial times that exponential. So that might make it easier to take the next derivative using product rule. So differentiate the polynomial, differentiate the exponential, factor out the exponential, and then we get, let's see, 4ax plus 4a. Beautiful. So we have all the derivatives we need. So now we plug into the original. So you have y double prime plus y prime minus 6 times y. And that should be equal to the right-hand side. Okay, so the exponentials cancel. And then we can combine the x terms. So 4, 6, minus 6, so that's 0 ax. And then all the constant terms. So 5a. So 5a has to equal to 5. So a is 1. Okay, so we find a particular solution. So the general solution to the non-homogeneous equation is our homogeneous part, so this guy, plus our particular part. Now for the third case, just to reiterate here the point. Now, so our particular solution, we're going to first assume looks just like a multiple of that exponential, but then we notice that this particular solution can be combined with something in the fundamental solution set. So to guarantee that the particular solution is independent from anything in the fundamental solution set, we're going to suffice this just to multiply this by x, right? So, and then we would differentiate and solve for a. So let's look at more. We're going to combine. So I don't think we probably won't be able to finish this. So next time I'll summarize. Right, I'll do more cases and I'll try to get a nice kind of formulaic summary of this method of undetermined coefficients. But for now, I'm just using concrete examples to motivate the formula so they don't look foreign when we see them. All right, so suppose we have y double prime minus 6y prime plus 9y. Okay, and that's equal to some function of x, which is non-zero. So let's make it e to the x, yeah? And then compare that to what happens. We have e to the 3x. And then compare that to what happens when we have x times e to the 3x. So here we can get a fundamental solution set for all of these. I'll just write down the characteristic polynomial real quick. This factors into r minus 3 squared. So we have a repeated root, right? So we know the fundamental solution set is e to the 3x, and then x times e to the 3x. So we know that homogeneous solution here is just some combination of the functions in the fundamental solution set. All right. So now we're going to do the particular solution here. Okay. So we have a simple exponential on the right. We're going to assume that our particular solution is that exponential. And then we check that this form, right, this particular solution is independent of everything in the fundamental solution set. And indeed, it is, right? You can't combine those. So all we have, so that's a good assumption here. And then we differentiate a couple times and plug it in. Y double prime minus 6 times y prime plus 9 times y. So we get 5. So 4a is 1. So a must be 1/4. So our most general solution here then is the homogeneous part plus this particular part, which is independent from everything in the fundamental solution set. So let's look at this next case. So we assume that the particular solution looks like a multiple of the right-hand side there. But then we notice that e to the 3x is alike, right? It can be combined with something in the fundamental solution set, e to the 3x. So to guarantee independence, all we have to do is multiply that by x. And then we say, well, does that work? So is the particular solution linearly independent from the fundamental solution set? Well, not quite, right? Because we have x times e to the 3x, and that's what we have here. So those are like terms. They're not linearly independent. So that's okay. all we have to do is multiply by the next highest power of x, so x squared. And this is just an assumption for our particular solution, and it just turns out to work. Okay? And it's now linearly independent from everything in the fundamental solution set. So now we're going to determine this coefficient by differentiating. A little housekeeping here before the next derivative. If you're wondering what I did there, just as a side note, that if you have polynomial times exponential, you always, using product rule, you get p prime, and then in turn differentiate the exponential. So if you do enough of the, if you have polynomial times exponential, you learn soon enough that that's the pattern here. So that's what I was using. All right, so I'll just clean this up. All right, and then we have we plug these derivatives right into our original differential equation. Y double prime negative 6 times y prime plus 9 times y is equal to the right-hand side. Exponentials go away, and now we can combine these. We have the x squared terms, so that's 9 minus 18, it's negative 9 plus 9, so we get 0 ax. The x terms, we get 12, well, we get 0 ax. And then we have the constant terms, so 2a. So a has to be a half. So our particular solution using the method of undetermined coefficients is a then x squared times theta. So our most general solution then to the non-homogeneous equation is our homogeneous part plus our particular part. All right, so notice that we multiplied by just a high enough power of x to guarantee that everything in our particular solution is independent from everything in the fundamental solution set. Let us do the third example. Okay, so I'm just gonna write down the fundamental solution set. All right, so now our particular solution foremost is going to be, okay, so this is where you get a polynomial times an exponential, okay, on the right-hand side. So this is the form poly times exponential, simple exponential. Okay, so now what degree is this polynomial? Well, it's first degree, right? Or first order, I guess. It's linear. So when we assume our particular solution, we have to assume a generic form of the right-hand side, or a general form. So the generic form of first degree polynomial is ax plus b. And then we have our exponential. Right? So when you have that polynomial part on the right-hand side, you start assuming a generic form of it. So some first degree polynomial unbeknownst to us. And now let me multiply this out to make a point. So now we want to know whether this is whether everything in every term in our particular solution is linearly independent from anything in the fundamental solution set. So we say, well, no, e to the 3x is a multiple of that, right? This can be combined with that. And the e to the, and then x times e to the 3x is like that. So neither term is linearly independent from everything in the fundamental solution set. So we can try to multiply by a power of x here, x squared and x. So then you ask yourself the same question. Is each term in my in my particular solution independent from everything in the fundamental solution set? So the answer for this term is yes, right? This cannot be combined with anything in the fundamental solution set. However, the second term is not fine because x times e to the 3x can be combined with the second function in our fundamental solution set. So it looks like you should, instead of multiplying by x, try the next higher power of x, x squared. So now this becomes ax cubed plus bx squared times e to the 3x. And now we see that both terms in the particular solution cannot be combined. They're linearly independent from everything in the fundamental solution set. So that's our final assumption about the particular form. So now we would have to differentiate this a couple times, plug it in, and solve for A and B. And we'll have to continue this example next time. Again, next time I want to provide a nice formulaic summary for this method of undetermined coefficients. And but generally, right, you have this constant coefficient business going on. And then you have on the right-hand side some function of x. So you get your fundamental solution set. And by the way, the right-hand side, this is only polynomial times a simple exponential, e to the ax, and then either sine or cosine. We haven't, some combination of sine and cosine, and we haven't looked at that yet. But then you assume the most, for your particular solution, you just assume the most general form of a polynomial on the right-hand side, or generic form, and then if you have any exponentials, and then a combination of sine and cosine. But you then have to guarantee that every term, right, not just right, every term is independent, it's unlike with anything in the fundamental solution set. And you have to multiply by the smallest power of x. So let me say, so this s is the smallest power, which would make every term in the particular solution independent from everything fundamental solution set. And then that's going to multiply some generic form of g. And we'll keep doing examples because we still have to look at sine, cosine. What if you have polynomial times sine and cosine? What if you have polynomial times exponential times sine and cosine? Well, I feel sorry for you then in terms of how much work you need to put into determining your undetermined coefficients for your particular solution. Thank you.